Welcome. We are back with another research paper implementation. In the fight against glaucoma, precision in analyzing retinal images is crucial. Today in this video, we are excited to explore a research presented in the paper which is titled UNet Combining UNet and Transformer for Joint Optic Disc and Cup Segmentation and Glaucoma Detection by Rakshanda Hussain and Ritam Basak. So let's start with the problem statement. Glaucoma remains one of the most significant causes of irreversible blindness around the world, affecting millions of people. Early detection is critical to managing the disease effectively and preventing vision loss. To achieve this, we need precise segmentation of the optic cup and disc in retinal fundus images. However, traditional segmentation methods face challenges, particularly in generalizing across diverse datasets. These methods often struggle due to the limited availability of comprehensive benchmark datasets, which impact their reliability and accuracy. In this research paper, the authors introduce a transformer-based model aimed at enhancing this segmentation process. The study addresses the critical need for reliable and generalizable segmentation methods in glaucoma diagnosis. Now that we are familiar with the problem statement, we can move to the next section, which is the dataset. In this research paper, the models were trained on 3 datasets, and we have replicated the implementation with one of them, which is the Drishti GS dataset. It is a specialized collection created for glaucoma detection. The Drishti GS dataset is crucial in the field, offering a well-recognized benchmark for assessing the effectiveness of segmentation models. Its high-quality images and precise annotations allow us to rigorously test our model's ability to accurately segment the optic disc and cup, which are critical steps in detecting glaucoma. This dataset comes from the Medical Image Analysis Group at IIT Hyderabad and is designed specifically for glaucoma detection. It includes 101 retinal fundus images divided into 50 training images and 51 testing images, and all of them are annotated by expert ophthalmologists to mark the boundaries of the optic disc and cup. These images are high resolution, ensuring the detail necessary for precise segmentation, and are stored in PNG format with each image paired with its corresponding annotation mask. This dataset's quality and specificity make it a valuable resource for training and evaluating the model. Now that we are familiar with the dataset, we can move to the next section where we will be discussing the steps that were taken for the implementation. So let's walk through the key steps we took in replicating the research paper from data pre-processing to model evaluation. So the first step was data pre-processing, which is crucial for ensuring the quality and consistency of the data used in our segmentation model. First off, we started with image resizing. So each retinal image along with its mask is resized to a standard dimension of 224 x 224 pixels. This uniform size is essential for maintaining consistency across all images and ensuring that the model can process them efficiently. Following this, the next step was normalization. We applied normalization to the images to standardize pixel intensity values. And next, we created the binary masks. To facilitate the training process, the masks are converted into binary format. This transformation simplifies the segmentation task by converting the pixel values into distinct classes, typically foreground and background. These pre-processing steps are designed to prepare the data for optimal performance with a UNet model, ensuring that the input is clean, standardized, and ready for the segmentation process. Next, also, we would like to highlight that it's important to note that the original paper does not provide specific details on the pre-processing steps that were used. As a result, we have applied standard pre-processing techniques commonly used in image segmentation tasks. Now we move on to the next step, which is model implementation. In this step, we defined a model which is UTNet. This innovative approach combines the strengths of both UNet and transformer architectures to enhance the segmentation of optic disc and cup in retinal images. Here's how we approach the implementation. Our model integrates UNet's encoder-decoder structure with the transformer mechanism. The UNet component excels at capturing local features and detailed boundaries, while the transformer enhances the model's ability to understand contextual information across the entire image. By combining the robust feature extraction capabilities of UNet with the contextual understanding of transformers, UTNet offers a powerful solution for precise segmentation in retinal images. Once we were ready with the architecture, we moved to the next step, which is train test split. We split our dataset into training and testing sets with 50 and 51 instances of data in each. This step is crucial to ensure that our model learns from a subset of the data and is then evaluated on unseen data, allowing us to measure its true performance. Once we were done with the split, we moved to the next step, which is evaluation. To assess the performance of the model, we made use of several key metrics like dice coefficient, accuracy, and F1 score. So the dice coefficient measures the overlap between the predicted segmentation and the ground truth. A high dice coefficient indicates strong agreement between our model's predictions and the actual boundaries of the optic disc and cup. We also calculated the overall accuracy of the segmentation to understand how often the model's predictions were correct. Also, we made use of the F1 score, which combines precision and recall into a single metric, providing a balanced measure of the model's performance. It's particularly useful in evaluating how well the model identifies the true positive regions of the optic disc and cup. These evaluation metrics help us to confirm that the UTNet model provides robust and accurate segmentation of the optic disc and cup, making it a valuable tool for glaucoma detection. Once we were done with these steps, we arrived at the result. So in the next section, we will be discussing the results. We can see that the original paper reported impressive dice scores of 97.4 for the disc and 94.9 for the cup, along with an accuracy of 99.84%. However, when we ran our implementation, the results were slightly lower but still strong. On the training set, our model achieved a dice score of 93.12 for the disc and 85.93 for the cup, with an accuracy and F1 score both at 99.87%. When tested on unseen data, the model produced a dice score of 88.94 for the disc and 85.78 for the cup, with an accuracy and F1 score of 90.46%. These results highlight both the effectiveness and areas for improvement in our approach, demonstrating the model's potential while also acknowledging the challenges in matching the paper's performance. If you are inspired by this demonstration and would like to leverage our expertise for your own research or projects, don't hesitate to reach out to Codersarts. Whether you need help with data replication, machine learning models, or any other technical challenge, our team is here to support you. Please like, share, and subscribe for more insights into how technology can transform healthcare. You can reach out to us via our email ID, which is contact@codersarts.com, or you can visit us via our website, which is www.codersarts.com. You can also find our Facebook, Instagram, and LinkedIn handles in the description box below. Thank you for watching the video.